Okay, we're starting Bronsted-Lowry acids and bases today. The acid is a proton donor, and the base is a proton acceptor. And we had everybody write these down, and we will continue in just one moment. You need to write them down now, so stop the recording. Okay, I hope you spent the time to write that down. Now, again, Bronsted-Lowry acids and bases. The conjugate acid and the conjugate base have very specific meanings. And so what you should do right now is stop the recording and actually write down these definitions. Okay, this page, don't bother to copy unless you want as you're watching the video. I'm not having the class do it, but I just wanted to give you a typical conjugate acid-base, conjugate acid-base experience here. So if you look up here, you're seeing the actual acid. Remember, the acid is always going to be on the left side. Let's go back here to these definitions, though, and let's do a split screen, and let's compare these guys. Okay, if you look at the left-hand screen at the top, you'll see acid's a proton donor, and the conjugate acid is the guy that receives that donated proton. And then the base is the proton acceptor in blue, and the conjugate base is what is left of the acid after donating the hydrogen. Now, look down below that, and you'll see on the left-hand screen, it says the left-hand screen has these guys are on the left side. You'll see that written right down here. And on the right side, you'll see down here, these guys are always on the right side of the equation. So we're going to try and give you the idea here of why we call the guys on the right conjugates and why we call the guys on the left just acids and bases. Okay, so as we go back here now, let's get out of the split screen mode. At the bottom, what I've done is a little diagram to give you the idea, I hope, that you'll understand. Let's put it that way. The neutral atom has an electron. That's the guy on the periodic chart. He has no charge. We're looking at this guy right here now. On the right side of this, that's also hydrogen, but that hydrogen, you can see we have that positive charge there. And you'll notice on the ring here, which is supposed to represent the outside of the atom, there's no electron. And what that means is that this ion is a very different kind of a little dude. He's lost an electron. We also call him, or he is AKA, also known as a proton. Right there. Okay. Now, let's carry on. Now we get to see how all of this actually happens. This isn't real, but it's more graphic than what we do when we write the symbols. So, let's call this guy right here, let's call him the base. And we'll call this guy up here the acid. And what I'm going to do is get rid of the arrows now, so I can go ahead and manipulate them. Remember, the guy in the lower left is the acid. Okay, so the acid is the proton donor. And the proton donor is coming over here to the base. Only on the other side of the equation now, we call this guy is called the conjugate base. Remember, he was the acid. He is what's left after he donates the hydrogen. Okay, over here, this guy here was called the base because he accepts a proton. Well, here he is. Now he is referred to as the conjugate acid. And you can see what's going on a little better than when we just write the equation. And now we're going to see the same thing in an actual Bronsted-Lowry representation of how an equation works. Here we go. Let's get rid of these guys so we can take them as we go. And we're starting out with two water molecules. And you say, hey, what is this? Two water molecules react with each other? Yes, they do, all the time. Every single little drop of water on the face of this earth is doing this back and forth that we're going to write down that we saw in the prior screen. Okay? Exactly the same. Okay? Going back and forth. I'm using my fingers going back and forth as I'm talking to the class. I'm referring to this back and forth operation right here. What do we say about equilibria? They are, starts with a D? E, Y, N. Dynamic. Dynamic. Okay, so they are dynamic. That means that they're constantly going back and forth between what you're going to see as the conjugates. So, look at your definitions as I walk you through this one. And then I'm going to do a second one where we're going to reverse the whole process. But we'll start with the acid. The acid doesn't have to be first, but in this equation I wrote it first. So this guy right here, the water, is called the acid. The base here is called the base. Yeah. The blue dude. There we go. I'll get it out. So our blue water is the base, and our red water is the acid. And now the acid, I'm going to define acid now. Acid is a proton donor. And an acid, after he donates the proton, becomes the conjugate base. Now I want you to think for a while, what in the world is going on here? See if you can figure out who that species is going to be. So, I hope you understood. Yeah, if you pause the recording, if you didn't, pause it now, and see if you can figure out who that is. Okay, if you got this, you're on the right track. Okay, that's the old familiar hydroxide ion. And you'll notice, if we go back to the acid over here, this guy's our acid, this guy's our base, and now this guy is the conjugate base. So the red water on the left becomes the blue hydroxide on the right, because he lost a proton. And let's go back and verify that again. On this page, let's go back and do that all over again. You see? Here is that water on the left that was in red, and he's called the conjugate base. And now we're going over here. I'm sorry, he's the acid. He's the acid because he's going to do what I'm doing right now. Okay? And he donates that hydrogen. Now he's called the conjugate base. And he's conjugate because he's on the right side of the equation. He's still a base. But because he's on the left side of the equation, or on the right side of the equation, we call him the conjugate base. And that's our hydroxide ion. Now, the next dude, the base on the left, a base is a molecule that accepts a hydrogen ion, not a hydrogen atom. And so I'd like you to stop the recording for just a minute, see if you can figure out what that guy's going to look like. Okay, one of my students not only identified it, but he also knew what the name of this dude was. So let's look at it. This now is H3O. Yes, the recording is on. And we're going to have a 1+ charge on that dude. And let's see why these charges show up. But first of all, let's label the guy. Okay, this is our conjugate acid, and H3O is AKA, also known as hydronium. Hydronium, hydronium ion. This is what actually exists in the water. There is no such thing as hydrogen ions except for a nanosecond. As soon as hydrogen ions leave a molecule, those hydrogen ions grab onto water and they become the hydronium ion. And let's look back here again and see in my little example. Okay, this guy on the far right, we call the conjugate acid, is got 3 hydrogens around it. Okay, now let's look at the charges. Let's add them up. How many pluses do we have here? Coral response? How many pluses? 3. How many minuses? 2. 3 minus 2 is? 1. And so the overall charge here is 1 plus. Right? And how many pluses here on the conjugate base on the left side? Okay, 1 hydrogen carries a 1 plus, and the oxygen is 2 minus. What's the net charge? 1 minus. That's where those negative and positives come from. Okay, because when the proton leaves, that was a source of a positive charge. And so when he goes away, we're going to have more electrons than protons. Because oxygen has 6 protons in his nucleus, and with the proton out there, we got 1, and so oxygen was balanced before it became an ion, and it's not balanced after it becomes an ion. So that's the ion that is taken on the hydrogens for the oxygen ion. Okay, so we've got this now. Let's look back here, and we are going to reverse the process. And now we got to think a little bit. The hydroxide that was up here on the top is the same hydroxide as this guy. No difference. But now, what are we going to call the hydroxide that's on the left side of the equation?
The base.
He is the base. He is no longer the conjugate base. And let's go ahead and move this down just a little bit. I'm going to need some room for my lines. And what are we going to call the H3O? This is the acid. Yes, it is. No longer the conjugate base and acid as they were up here. They're the same things. There's no difference. The only difference is that we wrote them on the left side of our equation. And so for purposes of understanding what we're talking about in a balanced equation, we use the straight acid and base designation for the guys on the left, and the conjugates are always going to be on the right. So let's go ahead and take our acid. The acid is what? A proton what?
Donor.
Donor. And what is the base? A proton acceptor. Okay, so over here, that H3O becomes H2O. And that dude is the base. The conjugate base. Conjugate base. And the OH becomes what? Yeah, this guy's going to become the acid, but it's still H2O, but we call it a conjugate acid. All right. Is this starting to make a little bit of sense? I hope.
Yeah.
All right, let's move on. Here we go. Let's get rid of all these guys and take them a little bit at a time. So we start out with, can anybody figure out what the NH3 is? It's going to be an acid or a base? Based on its color?
Base.
Yeah, sure. Okay. The NH3, we're talking about this guy right here. That's going to become his actual name of the molecule, common name is, anybody know?
Ammonia.
Ammonia, sure. So we're talking about ammonia in water, okay, the ionization of ammonia in water. And this guy is going to be our acid. So let's go ahead and let you have 2 minutes to complete this equation. So stop the tape now, or stop the recording now, and see if you can write the right side of this equation. And label it. Well, who's the conjugate acid? Who's the conjugate base?
You have to follow the lines and everything.
In case you missed that, it was the lines and everything.
Okay.
Yeah. A lot of people got it right. This is good. Okay, let's carry on. Okay, here's. No, it's not. Okay, now over here. What did I just do? Who is this guy?
NH4.
No. Over here.
Base.
He is the base. Okay. And if he's the base, the water has to be the acid. Excellent. And now the ammonia base. I got the question while we were doing it in class. How do you know what they are on the other side? Well, whatever they are on the left, like the ammonia is a base on the left. Because he's a base, he's going to become a conjugate acid over here. And so he has jumped camps, hasn't he?
Yeah.
He's become a base. He was a base that became an acid. And the acid is going to become a base. So let's go ahead and write our NH4. And because he picked up a hydrogen ion, he was neutral before, now he's got to be a 1+. And you can write this plus or 1+ either way. They're both correct. And then we'll get the water. We'll get him over here. And what is he going to become? He was the acid. He's going to become conjugate base. Yeah, conjugate base. And now over here, he's going to look like who? What is his formula going to be? OH minus. Yeah. Don't write HO because this is the hydroxide ion. It's just a convention. We always write hydroxide ion as OH. It doesn't make it wrong. It's just that's the way we normally write it. Okay? So we're good here.
What if you wrote H4 and 1+?
No, you definitely don't want to do that. No, not with ammonia and the ammonium ion, which is what we have here as the conjugate acid. Okay, the ammonium ion is always written with the nitrogen first. Yes.
Is it weird if it starts off as a base, it always has to turn into an acid?
It's going to turn into an acid. Yep, absolutely, guaranteed.
One question. Does the conjugate word here same as in math?
No.
No, it's like way different.
No, don't think that. No, this doesn't apply to math.
Yeah. Like same word. Is the base always the first one?
No, base can be first or second.
How do you know?
Now watch it. You always tell by what happens to it on the other side. Now let's think through this. We know right now that ammonia is a base, but if we didn't know that, we would look at the NH3 and see what nitrogen has on him on the other side. That's the way I do it. And when you look on the other side, he's got another proton, which means he accepted a proton. And so that makes him the base automatically. And if you look at water, and by the way, water you can always write this way, HOH. And that kind of brings us back to this other slide that I was doing earlier, where we had the, where is it? Where are you? There it is. Okay, right here where we were playing with the stuff going back and forth. Okay. That we know because we saw it move. Okay. But let's say what you're looking at on the screen right now is the left side of the equation. And now we look on the right side, and if you didn't see me move that hydrogen, you could still tell that the water on the left is now minus okay, and the water on the right is plus, okay. He has actually transferred a charge to the other side in the form of a proton, okay, and now on the right side he becomes the conjugate acid, and this guy becomes the conjugate base. The base is always going to be the guy that gives up the proton, and so in doing the giving up of a proton, he's going to have one less proton on him on the other side. So now I'm looking on the left side of the equation, we know that left-hand water was going to be the acid. Yeah, Arvin, did you have a question?
On test, are we gonna have like pictures like this?
No.
No.
God, don't you wish? Now let's have you actually look at this guy in reverse. Let's see, I think I should bring that back. Yeah, there we go. Okay. As you look at this now compared to this, the guy on the bottom, you'll see, just like with the water thing, we had the ammonia and the ammonium ion and the hydroxide ion were conjugate acid and conjugate base. Okay, we're talking about back up here. Now we're looking at the same guys down here, but now we call them something different because they're on the left side of the equation. Okay, so let's look at this side by side now, and maybe this will make a little bit more sense overall, I hope. Let's get this up and this, and just kind of get some of these extra arrows out, and let's just count it back. And now let's look at the right-hand screen. If you look at the right-hand screen, you see ammonia on the left as the base. When we go the opposite direction, water becomes the base. What's left of the water was the hydroxide ion. So that hydroxide ion that we saw on the right side in the top of the frame, this guy, is now sitting here. And this guy is now sitting here. And as such, they lose the conjugate designation, and now they are just straight acid and base. And as they go back to form what was the base and the acid to begin with, you'll see that the base now is called a conjugate base, this ammonia here, and this is called the conjugate acid. Right? So that's how that worked. And let's go back on these definitions just a moment again. So now we see the Bronsted-Lowry acid base guys, and let's just so now let's take our base and notice this is kind of fun. We keep going here with red because it's going to become an acid. So the base becomes the acid, and the acid becomes the base in the other frame. So again, reinforcing the idea that the acid becomes a base, but when he becomes that base, we call him the conjugate. And likewise, the base became an acid, but when he became that way, we called him a conjugate. All right. This pretty much wraps things up. I hope you find this helpful. I decided to continue the recording for just a little bit here to see if we could actually get an understanding really settled down in our minds. Let's look at our first equation here, and I'll kind of cover up the others so that your mind can focus. So we see ammonia as our first reactant. Now, we know that ammonia, because of what we just did, we know ammonia is our acid and water is going to be the base. But if we didn't know that, can anybody figure out how I would tell?
Check the other side.
Check the other side. Perfect, Arvin. And so right here, if we look at the nitrogen and hydrogen combination, there's only two things it can be on the right side. It could be NH5 or NH what? It's 5 if it gains a proton. What is it if it loses one?
3.
Is there an NH3 there?
Yeah.
Okay, so it lost one, didn't it? If it lost one, it has to be an acid, because Bronsted-Lowry, the acids are the proton donors. So what's our conjugate acid-base pair? Ammonium ion and, no. The acid-base pair. This guy's the acid, this guy's the conjugate base. Okay, so that's the pair that they're talking about here. Identify the conjugate acid-base pairs in the following reactions. Okay, so again, if we didn't know that hydroxide was a base, is there a OH on the right that has an extra hydrogen or one less hydrogen? Extra. So this guy became the proton what? No, it was the acceptor. Remember, the donor gives. Today, a lot of you, some of you, anybody gave blood today? Anybody give blood today? I've had some in my other classes. Anyway, if you gave blood today, you would be the donor, and you'd donate 1 pint, because that's all you can donate. Yeah, some do. And so this guy was actually the acceptor. He accepted it, and he got the H2O. So this is the base and its conjugate acid. Okay, let's go down here. Aside from the fact that we know that HBr is hydrobromic acid, aside from that, could we find bromine on the other side? Is he there?
No. Yes.
Okay, on the right side, it's bromide ion. And so what happened? Did he gain or lose?
No.
So what does that make him? Okay, that's your acid. And what is this guy?
Conjugate base.
Conjugate base. Okay, and water is
Base.
base because he gained one, because over here it's H3O instead of H2O. Are we feeling confident here?
Yes.
Good. Okay, we'll go ahead now.